Okay, so today I will present you an ongoing work called LLM4Docq, which is about leveraging LLM to generate doc strings for the MathComp library. It's a work with Jules Viennot and Cyril Cohen. And let's start with a little bit of context. So MathComp is a library of formalized mathematics in Roc, which doesn't have any doc strings, yet we know that doc strings can be useful for learning the library, for contributing to something, and with some dependence, some previous dependencies. And it can also be very useful for the deep learning community because having natural language annotation to some formal statement can be very useful to train model to do formal things. The thing is, adding annotation to MathComp is a lot of work because there is like 10,000 of elements to annotate individually. So in this work, what we try to do is to automate some part of this effort to be able to do it in a finite amount of time. We have some final goals that are not just about these doc strings. First, having all this data, we were able to develop a natural language search embed in the IDE. And also, we plan to train a model to do auto-formalization and to do annotation of formal statement based on these datasets. In another work with Guillaume Baudard and Marc Lage, we actually use this natural language search tool to use an LLM to do automatic theorem proving. And so the LLM is able to use this language search tool to do premise selection. So let's start with this natural language tool. So maybe a bit of an introduction of embedding model. So to do it, we use what we call an embedding model. So an embedding model is a model trained to map text to point in a vector space with the property that if texts are semantically close, then the obtained vectors are aligned. So if you do the dot product between your vector, then it will be close to 1. If they are semantically different, then the vectors will be almost orthogonal. And based on this model, what we can do to develop a natural language search is pre-compute all the doc strings, and then at runtime, compute the embedding of the query of the user and do an approximate nearest neighbor, use an approximate nearest neighbors algorithm to find the closest doc strings. So this way, we're able to develop such a tool. So very quick demo. So if, for example, you're looking for a property about the injective function and order relations, then you can write this sentence like injective function preserve property of order relations. And what you can get with this tool is a list of a few lemmas and notation and definition that are related to this property. So this is all done locally with a computer that doesn't have any GPU, but it requires some amount of RAM to work well. So you need like 10 GB of RAM, and you can query it, and in a few seconds you get these suggestions. Okay. So now that we have this tool, the natural question is how to measure the performance of this tool. And what we need to do it is a dataset containing pairs of query and target lemma. And then we're able to check if the target lemma is in the top K of this given by this tool. So to generate this benchmark, what we did is we extract a diverse set of theorems and proofs using, for example, BM25. And then we select randomly a step in the proof of these theorems. And then we ask an LLM, given this context, given this theorem, and given this target lemma, what could be a query, a natural language, query written in natural language that could correspond to the user need at this point. And this way, it was very easy to actually compute this, to generate this benchmark datasets. And we also did a few audits, so we were like okay with this data set. And here are some examples of this data set. So here we have like the queries about the divisibility of dimensions of vector subspaces. The target lemma is this one. And the docstrings that we already have is this one. And with this tool, we are able to retrieve this in the 5th position. Another one is the one that I already showed you about the order relation preservation using injective function. And the same thing, the rank is actually not so high, so it will be usable as it is right now. If we do it more systematically, we obtain these results. So if you look, for example, at the abscissa x is equal to 20, you obtain 92% of accuracy, which is mean that in 92% of the case, your target lemma will be in the top 20 of the given premises. We test a bunch of embedding and different models, and the one that was the best was this 4 billion parameters embedding model from Cohen. There is still some limitation. First, we are not just evaluating the quality of the docstrings, but we are also evaluating the quality of the embedding model. That's why the 4 embedding model give different results. But we are also evaluating the ability of the LLM to formulate good queries. And even though we audit it and we check that the queries were all right, there is maybe too much homogeneity. Maybe some real-world user won't formulate things as the LLM did. So there is maybe this gap between real-world usage and what we are evaluating right now. And maybe in practice, instead of looking at the 20, 30, 40 best 40 first result given by this tool, maybe, for example, it would be more efficient to do multiple queries. So that's things that we are not trying to evaluate right now. Now, I will talk more about the creation of this data set and how we are trying to have the best docstrings for MathComp. So the overall pipeline is the following. We use an off-the-shelf LLM. So here is a GPT 4.1 to generate docstrings. We have some prompting that I will talk a bit more in the next slide. Then we do partial audit done by MathComp experts. And based on this partial audit, we do a data analysis and we update prompts in the hope that the next generation of docstring will be better. And at the end, what we aim is to have a 95% of docstring that are judged acceptable by experts when they are uniformly drawn. And the overall pipeline costs 25 euros for a full run to generate every docstring. So it's kind of okay to do it multiple times. For the generating step, we have 3 parameters that we can play with to improve results. The first one is the general instruction we give to the LLM. So the aim of this docstring, for example. We also give to the LLM some context about the element that he has to annotate. And so these things right now has been automatically generated. So there is maybe some error right now, and that's something that will improve for the next version, for the next iteration. And also some generic examples of expected docstrings in some cases. And now to audit it, as I already say, we have an online interface to gather expert reviews, and we manage 3 cases. The first one is whether the docstring is acceptable, does it need improvements, or is it incorrect? So the user interface is this one. You have the location of the element you have to review, you have the code, you have the synthetically generated docstring, and you can check whether it's acceptable, needs improvement, or is incorrect. You can give feedback, and you can also write an improved version. If it's acceptable, then you don't need to write an improved version, because if it can be improved, then it's not acceptable for us. And So in this example, the notation that is introduced is the notation about the generated subspace from a set and an element U. In this case, the docstring is okay, it's acceptable. But if, for example, the element U and the variable E is not defined, like in this new example, then this will be will have to be categorized in the needs improvements because it needs some additional information. And if this example, if the LLM thought it was, for example, the Japanese bracket notation, then it will have to be categorized as incorrect. So yeah, this is the three cases we're trying to handle with this online interface. So we already did the first review based on 600 reviewed docstrings. And among them, 92% of them were judged acceptable. 15% of them need improvement, and 3% of them are judged incorrect. So it's encouraging as a first iteration of this pipeline. In the needs improvement category, we actually have three cases that are possible right now. The first one is the phrasing that is inconsistent in a same source file. For example, the way the docstring is written is not uniform from one element to another. So it's half the cases. The other case is when it's too verbose. Sometimes the LLM can write some unhelpful information, which is really not what we want. And sometimes it can lack precision. So, for example, in the previous example I give you, if the LLM forget to tell what is the E and U variable, then it lacks precision. So the next iteration is in preparation. So basically, what we do is to audit each prompt with MathComp experts. We're also trying to change the set of rules and the examples we give to the LLM to have more homogeneity, because this phrasing issue seems to be quite important. And yeah, the final goal we have, the final objective we have is this. Is to reach this 95% of acceptable docstrings. And based on this data set, what we aim to do is to train two models. The first one will be an annotator model that will be trained to predict a docstring given a file context and a formal statement, which could be helpful, for example, during the development of a new statement in MathComp. But also to train a model to predict a formal statement given a file context and docstring. So somewhat related to auto-formalization, but maybe much easier because the model will have access to much more information and it will be less ambiguous problem. So that are the two targets we have with the final data set. So thank you. If you want to contribute to LLM4Docq, please reach out on the Rock Provers ULIP at Théo Stoskopf, or by mail if you prefer. And please look at the GitHub page, the GitHub repo, if you are curious about this project. Thank you.